All right, so the intuition is that we look at the grammar rules and we look to see what tokens show up to the right of a grammar symbol, and that will give us the follow set. But so let's actually do a really, really simple example first. I will erase this. Here's a very, very simple grammar. This is my grammar of equal number of zeros and ones. 0 to the n, 1 to the n. Okay, 0s1, or yeah, that's good, or epsilon. So what can follow s? 1. Okay, so well, 1 can follow s. 0 can't follow s in this case. I want to make an aside. I want to augment this grammar slightly. Again, not grammar, augment the definition slightly. Bear in mind that the reason we're computing follow sets is to help us figure out when to do reduce actions. Okay, that's the whole point. That's the goal that we're after. So sometimes it's also useful to know for which for which grammar symbols, I could see an end of file at the end of right after I've seen the grammar symbol. So if you think of the way the parser is working with the scanner, every so often the parser calls the scanner, invokes the scanner, gets a token back, works with the token, calls the scanner again, gets a token back, works with the token, and the scanner is what is giving it these tokens. Right? The scanner is giving it these tokens. Well, at some point, the scanner is going to say, that's it. There are no more tokens to be had. And that's actually a useful thing to know, because an accept decision is made by a parser when it has reduced the input sequence to the start symbol and there are no more input tokens to be read. So getting that end of file or end of input from the scanner is important. So in this case, what could follow s? Well, s is the start symbol. So once we've read everything that s could give us, another possible thing that could follow s is a $. Okay, so the augmenting over here is that also $ is in follow of s, where s equals start symbol and $ equals EOF. Okay, so this is by definition. Okay, once I've read in something that the start symbol can derive, what can come after that is the end of input. All right, so this was easy, and we can extend this to more complex grammars, but look at the thing that follows the start symbol. I'm sorry, look at the thing that follows look at the tokens that come after the grammar symbol, and that tells us the follow set. So now here is a slightly more complex grammar. This grammar, s goes to 0 and 1 or epsilon, this gave us the language 0 to the n, 1 to the n, right? Suppose I want the language of all strings that have an equal number of zeros and ones. How would I do that? What's the grammar look like? Well, let's go with something a little simpler than equal number of zeros and ones. I'd have to think about that. But so let's do something like all balanced parentheses. Okay? So grammar for balanced parens. So here's what a grammar for balanced parens looks like. S goes to, those are balanced parens. S goes to S, S, epsilon. Right? So here, I can do things like S goes, I can derive strings like, I can derive strings like that. How do I figure out what follows S? So here, I'll begin the computation by doing the easy part, and then you guys can give me follow of S contains dollar, well, that's easy, and it contains what? Right paren from there. And what? Left paren. Why? Because we know it does, right? Yes, you're right. It does. The left paren does come here, and intuitively, the reason I get a left paren is, think of a derivation. Let's work out a derivation. Let's do the derivation over here. Let me erase it here. Let's do a derivation. Here's S. S goes to S. S. This guy goes to left paren S. Right paren. Oh, look, that follows S. Oops. Syntax error. Right, so in this case, you're absolutely correct. Your intuitions are correct. I should have that in the follow set. My problem is that looking at the grammar, that's not obvious. It is obvious when I look at that particular derivation. And I can see the derivation is S goes to SS, goes to S. That's the derivation sequence. And then this can keep going. But the left paren follows the S. But it's not obvious from looking at this. So we need a little bit more machinery. Okay, we need a little bit more machinery to compute follow sets here. The question is, what's going on is this. If you think of this particular derivation, what's happened is what can follow S, what can follow this guy is whatever can begin this guy, right? So I take this guy and say, well, here's a variable. This variable can go off and derive all kinds of strings. And any token that could be at the leftmost position of that string will follow S. So here's something that where left paren begins a string that this guy could derive. And therefore, that token is in the follow of this guy. Does that make sense? Okay. Let me do a slightly more complex example. This one has S's, and the S's are playing a double role, and that can be confusing. So here's a slightly more complex grammar. S goes to A, B, C. A goes to AA or epsilon. B goes to B, B or epsilon. C goes to C, C or epsilon. All right, let's clean this off. Let's look at this grammar. Let's do some derivations out of it. S, A, B, C, right? So just for illustrating this point, I'm not going to go with leftmost to rightmost or anything. I'm going to do sort of random most. A, B, B, C. So from here, I can see that B should be in the follow of A, even though that's not obvious just looking at the grammar rules, right? There is no particular grammar rule where this token B appears to the right of A. I forgot to mention this. I should have said this much sooner. I'm using the convention that lowercase letters are tokens and uppercase letters are non-terminals. Okay? You could have inferred that by noticing what things showed up on the left-hand side of rules. But just for completeness, that's there. And from here, I can do another derivation step, and I can get A, B, B, C, C. And look, this guy appears to the right of B. So C is in follow of B, of big B. Right? Okay. So this is good. What? So the intuition is that if I can figure out those tokens that appear all the way on the left-hand side of what this guy can derive, B can derive B, B. Oh, look, there's a B over there. So that guy's in the follow of A. And C can derive C, C. So little c is in the follow of big B, and so on. Okay? Let's make things a little bit more complex. Here's a different production. I'm sorry, different derivation. A goes to, S goes to A, B, C. Well, let's suppose that B goes to epsilon. Because B went away. Now what can follow A? Little c. What's that? Little c or nothing. Yeah. Well, we'll have to figure out what to do with the nothing. Yeah, absolutely right. But little c. Now that's harder, right? Because if I look at the grammar, c is over here associated with c, and that's kind of far away from A. So let's generalize what these examples are showing. Really what we are after, and what that grammar showed us, and what this grammar is showing us, is that if I want to figure out what tokens can show up to the right of a dot, it's not enough to just inspect the individual productions and say, hey, let's find where the tokens are. That's necessary, but it's not sufficient. Okay? In general, what I have to do is I have to say, hey, look, here's a production. Here's my grammar symbol A that I'm interested in. Look at all the stuff to the right of it, in this case BC, and figure out what tokens could show up at the beginning of everything that these guys could derive. So the question really is, follow of A in this grammar is equal to the set of tokens that could start anything that the rest of this BC could derive. Okay, so i.e. the set of tokens running out of symbols here. Let's say the set of tokens little x such that BC together can derive x some alpha star. Okay? Have I managed to confuse everyone? What I want to do is I want to look at all of the grammar symbols to the right of A, and I want to ask, what tokens could I get if I started doing derivations starting from the sequence BC? I just started doing derivations every which way. What tokens could I get at the very beginning? So let's think of what tokens we could get. For this grammar, for this grammar sequence, here's the production, here's the derivation, S go to A, B, C. Now I want to know what follows, what could follow A. Let's do derivation starting from BC. Well, here's one. BC goes to B, B, C, and that goes off. And so little b is in the follow. It's in the follow of that guy. So that's one possibility. Here's another possibility. BC, B goes away. I use the rule B goes to epsilon. Goes to C, which goes to CC, and so on. Which means that this one is in the follow set. And there's a third possibility, which is that BC goes to C, which goes to epsilon. And we have to contend with that, and I'll hold off on that for just a second. Okay? But the key point that I want to bring up, that I want to emphasize, is that while the definition of a follow set says that, well, starting from the start symbol, just think of everything that you could derive. Look at the tokens that could show up to the right of the grammar symbol you're right of the variable you're interested in. That's the follow set. Well, in practice, computing it is not as straightforward. And we've seen that in these examples. We've seen it in this example. We've seen that left paren should be in there, but it's not obvious from looking at it. So the question we ask is, here's a production. Take everything to the right of the variable I'm looking at and ask, what tokens could this guy derive, that sequence derive? So before I can solve my follow set problem, before I can figure out how to solve the follow sets, I first need to figure out how to compute these guys. I first need to compute what tokens could show up at the beginning of anything these guys could derive. Once I've done that, then I can bring that out and apply it here. Steve? I don't. So the question is, do I normally include epsilon in the follow set or not? The answer is no. And the reason is that the scanner will never tell you, oh, I saw nothing. Right? The epsilon is the empty sequence. So the scanner will never tell you that. So if you think, again, all of this theory is fine, and we're writing lots of math notation with closures and enclosures and unions and set membership and all. But this is not, I mean, all of this math has a goal at the end, which is to produce these parse tables. So at the end of the day, this all has to be validated in terms of the parser interacting with the scanner. The scanner will never tell the parser, oh, I didn't see anything. So epsilon is not ever in a follow set. On the other hand, the scanner does tell the parser sometimes, there's nothing more to be seen. I've seen the end of file. So dollar is in follow sets sometimes. Okay, so in order to compute follow sets, I need to compute what can come at the beginning of something that a sequence of grammar symbols can derive. And that is important enough to have a name. It's called first sets. So just as this was a definition, here's a definition. First sets. Now, before I define the first set, let me tell you what the first sets apply to. As I had in that example that I've just erased, I can have a grammar where I might be interested in a particular grammar symbol, and I have to ask, what is the set of tokens that could be obtained in the first position of something that this whole sequence could derive? So first sets are defined for any sequence of grammar symbols. Okay? So the definition is that given a grammar, variables, terminals, productions, star symbol, and sequence X of grammar symbols. So that means that X is in V union T star. So X is any sequence of grammar symbols. Okay? First of X is defined to be the set of tokens, such that starting from X, I can derive a beta, where beta is in V union T star, which is to say beta is some sequence of grammar symbols. So again, lots of notation. Some people are comfortable with mathematical notation, some people aren't. So let's restate this in English. X is some sequence of grammar symbols. Okay? Could be empty, could be non-empty, could be a token, could be a variable, could be a whole bunch of variables and tokens. The first set is always a set of tokens. Actually, I'll modify that slightly, but for now, this is a set of tokens. And it's a set of tokens such that if I start with X and I start doing derivations, every possible derivation, I get the tokens at the leftmost position. These are the tokens that are in the first position of any string, of some string that X can derive. Not any string. Let me rephrase that. The first set for X is the set of tokens that are in the first position of some string that I can derive from X. Okay? And the reason I want to compute first sets is what? So I can compute follow sets. Why do I want to compute follow sets, other than give you guys a hard time on a Monday morning? Because I want to compute reduce actions. So that's the grail at the end of the, sorry, mixing metaphors here. That's the light at the end of the tunnel. What's that? It is. It is. Or they are. So now, the next time GCC parses your program successfully, you look at it with renewed respect. So we have to compute first sets. I should also say that the first set is, it consists of tokens. Just as we modified the follow sets a little bit to say that follow sets can also contain the end of file symbol, which is not, strictly speaking, a token. The first of X can also contain the empty sequence epsilon. So that's where epsilon can show up. So also, if X can derive the empty sequence, then epsilon is in first of X. Okay? All right, man, that's been a heavy mathematical lecture. We need algorithms. We need algorithms that you can convert to code. Because happiness is C code. What's that? That's not debatable. I refuse to debate that. So, what I want to talk about in the little bit of time that we have left, well, we can talk about algorithms today, or we can talk about algorithms Wednesday. This has been a pretty math-heavy lecture. So if you guys want, we can stop here today. Let's compute first sets. Okay. First set's actually pretty easy. Follow sets that give people trouble. Well, give ordinary people trouble, but you guys will have no trouble with it. See, now the bar has been raised. You can't disappoint me anymore. first sets are relatively easy. So I've defined this with respect to any sequence of grammar symbols, right? Any sequence of terminals, non-terminals, no matter how large. I'm going to break it. I'm going to give you an inductive definition. Translating that into code is not that hard, I assert. So first of the empty sequence, since I'm talking about the first of a sequence, the empty sequence is a possibility. That is the set containing just epsilon. And that comes from this clause of the definition. The empty sequence derives the empty sequence in 0 steps. OK, first of A, where A is a terminal, is just the set A itself. Why is that? No, I want someone else. Why is that? Will? Terminals can't be reduced to anything else. So the terminal can only derive itself because there's no other derivation possible. So that's all it is able to derive. OK. Suppose where x is a variable. OK, this is the hardest one, and it's not even that hard. If you can figure this out, the rest kind of falls out. So let's see. So first of x is a variable. Suppose I have grammar rules for x. X goes to gamma 1, gamma 2, gamma n. What's the first of x? Well, let's think of the definition. First of x is now a single variable with these productions. So what I want is the set of tokens I could find in the leftmost position in some derivation starting from x. Starting from x, some derivation. Well, if I'm starting from x, what can I say about these derivations? They've got to use one of the rules for x. So what can I say about, you have those rules there. So in this case, so let's look at the first step in the derivation for x over there. What can I say about it? You know this. Yes, Brian. What do you know?
It's like recursive. Isn't it going to be in the set of anything in the first of gamma 1, gamma 2, or gamma?
So the question is this recursive? And the answer is yeah. Yeah, it's an inductive definition. Sorry, say that again?
Isn't that just A capital X?
Is it A capital X? Oh, I'm sorry. I apologize. I'm going to get rid of the definition. We don't need that anymore. Sorry, I misled you. I lied. So I'm trying to compute first of x. X is a variable that's defined by these rules. So let's start deriving from x.
Gamma 1.
Gamma 1, all right.
Gamma 1 can derive, then we can...
X goes to gamma 1, Gesundheit. So x goes to gamma is certainly a possible derivative. What else could I have? Gamma 2, all right. Surprise me. What's the third thing we could do? All right, gamma 3, yes. Dot, dot, dot. That magic dot, 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 gamma n. And these guys go off and do their own thing, right? Gamma 1 goes off and derives. And eventually it derives, I don't know, A something. And this guy goes off and derives B something. So the something is some sequence of grammar symbols. What can I say about the first thing that could show up in the leftmost position for this derivation sequence? Eric is nodding in agreement. It's A? Yeah, okay. But maybe gamma 1 goes off in some other tangent too. And that could go off somewhere else. So what can I say about the leftmost token that could show up if I take this derivation step? You guys know this. Yes? It's the first of this guy. Exactly. That's exactly right. It's the first of this guy. Right? Okay. And you can see why. I start over here. And this is just the earlier problem that I had. I've just kind of deferred it. So it's the first of this guy. It can go this way, this way, this way, this way, whatever. This could be epsilon. It could be a single token. It could be multiple tokens, a variable. But it's at the end, it's all of the tokens that I could get in derivations every which way, starting from this guy. So if I went this way, what I would get would be what about this way? No, it's not.
First of gamma 2.
2, thank you. Keep you on your toes, Will. What about this one? N. Okay. Excellent. What can I say about first of X? Union of all this. Yeah. So it is, and just to indulge in some notation, it's union over I right? Good. Well, that is progress. We haven't gone there all the way, but we've made a lot of progress. So now, let's look at the definitions that I have. I've considered the empty sequence. I've considered the sequence of a single token. I've considered the sequence of a single variable. This really is the hard part. It took us a while to get our minds around it. Now the inductive step, first of a sequence of symbols. So all of these are the base cases, 1, 1, 1 symbol. So now if I can figure out what I have to do for a sequence of grammar symbols, then I'm good. So let's see. Picture time. Real simple example, okay? S goes to A, B, C. A goes to A. A1, A2. B goes to B1. B goes to B2. Okay? Straightforward grammar. So question. First of A, B, C. So let's look at this whole right-hand side. Well, let's suppose we start doing derivations. Okay? We had that picture that I just erased. If I start with A, B, C, and I start doing derivations every which way, I could go two ways. I could use this rule, or I could use this rule. A1, BC, A2, BC. And then this guy could go in various ways. What is the first of this sequence? It's A1 and A2, right? So in this case, it is the first of this guy. So that's equal to first of A. A1, A2. Right? Okay. Good. Make it a little bit more complex. Whoops, I didn't mean to erase everything. Now what's the first of A, B, C? What's that?
A1, A2, B1, B2.
A1, A2, B1, B2. So in this case, with this new grammar, because I introduced that, here's what can happen. I can start with A, B, C. Here are the possible derivations. I can go with A1, B, C, and this can go off. Or I can derive A2, B, C, and this can go off. Or I can go to epsilon, so I can derive BC, and this can go to B1, and this can go to B2. Okay, so in this case, how can I express it in terms of the first of the components? Well, I can say this is equal to, well, this guy's kind of obsolete, so let me take it away. It's equal to first of A union, because A can go away, union first of B, right? Suppose I said, oh, B can go away too. Suppose I throw that in. Now what happens? So then I get first of C thrown in. So let's come back over here. First of a sequence of grammar symbols y1 through yn. Let me get it started, and then I want you guys to finish it for me. So I do the easy part, and then you guys do the hard part. This is going to be equal to first of y1. First of y1 is in there. Then what?
Let y sub k be the first element in that sequence that does not derive epsilon, and then take the meaning of
All this.
from I equals 1 to k that y sub k.
That
The
sounds.
meaning of the first.
That sounds right, but it's more complicated than I can handle. So tell me what the intuition is that you're thinking of.
The intuition is that we're going to keep meaning all of those until we get one that can't derive.
Until we get one that can't derive epsilon. So suppose I had first of y1, y2, and suppose that y1 could derive epsilon, then I would also throw in the first of y2. And then I'd say, can y2 derive epsilon? If it can derive epsilon, then I'll throw in the first of y3. And I'll keep doing that until I get to something that cannot derive epsilon, and then I'll stop. OK? All right. So I haven't written this down yet, and I won't write that down today. What I'll do is when we start on Wednesday, I'll pick up this part you guys have figured out. This is good. This is the one part that remains to be done. And this is the one part. This part needs a little bit of work. Once we figured out how to compute the first for a sequence of symbols, then we'll know how to do this part. Right? Then we'll be able to compute the first for the right-hand side of the productions, because that's the same case as this. So then we'll be able to compute first sets. Once we can do that, follow sets will fall easily. And then we'll pop the stack way back, and we'll compute parts tables. And then what we'll do is, and this is something that I'm looking forward to, you remember when we began the discussion of bottom-up parsing, there was a little grammar. S goes to A, B, something or the other. And we did that example of how to do shift reduce. And a question that a number of people had was, wait a second, you're reducing with A goes to little b in one place, but not the other. Why is that? What's going on? So what I want to do is take all of this stuff that we've applied, actually go ahead and construct the parse table for that, and see if we can successfully parse that grammar. So that what we would like to have happen is that the table that we've constructed, just applying the algorithms we've seen so far, that the tables will tell us you should reduce here but not here, and we should get a successful derivation. So I'll see you guys on Wednesday. We'll talk about this.